Today we're going to explore one of the most profound experimental discoveries in 20th century physics. The discovery of superconductivity by Heike Kamerlingh Onnes in 1911. This discovery challenged everything physicists thought they understood about electrical resistance. In the early 1900s, Heike Kamerlingh Onnes at Leiden University was obsessed with one goal: reaching temperatures as close to absolute zero as possible. He had successfully liquefied helium in 1908, achieving temperatures around 4 Kelvin. With this capability, Onnes could now investigate how materials behaved at these extreme low temperatures. He chose mercury as his test material because it could be purified to very high quality. Now, what did classical physics predict would happen to electrical resistance as temperature dropped? Let me explain the theoretical framework that existed at the time. According to the classical Drude model, electrical resistance arises because conduction electrons collide with vibrating atoms in the metal lattice. These collisions scatter the electrons and impede current flow. The resistivity ρ equals m over n e squared tau, where m is electron mass, n is electron density, e is electron charge, and tau is the average time between collisions. As temperature decreases, the thermal vibrations of the lattice atoms decrease. This means fewer and less violent collisions with the electrons. Therefore, classical theory predicted that resistance should decrease smoothly and gradually as temperature dropped. The decrease should be monotonic and continuous. In fact, the simplest models suggested resistivity should be proportional to temperature. At low temperatures, you might expect something like ρ of T proportional to T. However, real metals always contain impurities and crystal defects. These provide temperature-independent scattering centers. So the actual expected behavior was ρ of T equals ρ0 plus AT, where ρ0 is the residual resistivity from defects, and AT represents the temperature-dependent phonon scattering. This is absolutely crucial. No known mechanism in classical physics could produce exactly zero resistance. Even at absolute zero, you would still have the residual resistivity ρ0 from impurities and defects. So with these theoretical expectations in mind, Onnes began his systematic measurements in 1911. He cooled his ultrapure mercury sample and measured its resistance at various temperatures. At first, everything looked normal. At 10 Kelvin, the resistance was measurable. At 8 Kelvin, it was lower. At 6 Kelvin, lower still. The resistance was decreasing smoothly, just as predicted. But then, as Onnes continued cooling below 4.2 Kelvin, something utterly unexpected occurred, something that would change physics forever. The resistance didn't just decrease gradually. It plummeted. It collapsed. At precisely 4.2 Kelvin, the resistance dropped precipitously to zero. Not to a small value, to zero. Unmeasurably small. Onnes was so astonished by this result that he repeated the measurement multiple times to ensure it wasn't an experimental artifact. But the result was always the same. Below 4.2 Kelvin, mercury had absolutely no electrical resistance. Let me give you some numbers to appreciate how dramatic this transition was. This wasn't a gradual decrease, this was a phase transition. The transition occurred over a temperature range of about 0.01 Kelvin. That's an incredibly narrow window. The sharpness of this drop was unprecedented. At 4.3 Kelvin, just above the transition, the resistance was about 0.1 ohms. This was easily measurable with the instruments of the time. At 4.1 Kelvin, just below the transition, the resistance was less than 1 microohm. It was below the detection limit of any instrument Onnes had available. That represents a drop by at least 5 orders of magnitude, happening within a fraction of a degree. Nothing in classical physics predicted this. This discovery created an immediate crisis for theoretical physics. Every known mechanism for electrical conduction completely failed to explain this behavior. First problem. In the Drude model, as long as there are any impurities or defects, there must be some residual resistance. You cannot get to exactly zero by any classical mechanism. Second problem. The transition is a discontinuous phase change, not a smooth decrease. Classical thermal physics had no framework for understanding such a sharp transition in a transport property. Third problem. Once in the superconducting state, the zero resistance persisted indefinitely. Once demonstrated that a current, once started in a superconducting loop, would flow forever without any power source. Modern experiments have shown that such persistent currents decay with a time constant exceeding 100,000 years. This is not just very low resistance. This is fundamentally zero resistance. Let me pause here and ask a question. What does it truly mean for a material to have exactly zero resistance? What are the implications? It means that electrons moving through the material encounter absolutely no obstacles, no scattering whatsoever. They move as if through a perfect vacuum. From energy conservation, if resistance is truly zero, then no electrical energy is converted to heat. The current carries energy without any dissipation. The power dissipated is I squared R. If R is exactly zero, then P is exactly zero, regardless of the current magnitude. This behavior implies that the electrons are not behaving as independent classical particles. They must be in some kind of collective quantum state that is protected from scattering. After Onnes' discovery, physicists spent decades trying to understand the microscopic mechanism. What could possibly cause this dramatic phase transition? Early theoretical attempts to explain superconductivity all failed. The problem was that classical physics simply had no tools to describe this phenomenon. The breakthrough came in 1957, when John Bardeen, Leon Cooper, and Robert Schrieffer developed what is now known as BCS theory. This provided the first successful microscopic explanation. The key insight was that electrons in a superconductor form bound pairs called Cooper pairs. These pairs behave as bosons rather than fermions. Now you might ask, how can electrons possibly attract each other? They're both negatively charged. They should repel, right? The answer lies in an indirect interaction mediated by the crystal lattice. When an electron moves through the lattice, it slightly attracts the positive ions, creating a region of enhanced positive charge. This distortion can then attract a second electron, so through this phonon exchange, two electrons can effectively attract each other, despite their electrostatic repulsion. The binding energy of a Cooper pair is given by minus h bar omega d times exponential of -1 over n0v, where omega d is the Debye frequency, n0 is the density of states at the Fermi level, and v is the interaction strength. This binding energy is incredibly small, typically only a few millielectron volts, but it's enough to create a collective quantum state. There's a beautiful empirical relation. The superconducting energy gap is approximately 3.5 times kBTC, where Tc is the critical temperature. For mercury with a critical temperature of 4.2 Kelvin, this gives an energy gap of about 1.3 millielectron volts. This is the minimum energy required to break a Cooper pair. Once Cooper pairs form, something remarkable happens. All the pairs condense into a single macroscopic quantum state described by one wave function. This superconducting state is described by a macroscopic wave function, psi equals magnitude of psi times exponential of I theta, where theta is a phase that is coherent across the entire sample. This quantum coherence is what protects the supercurrent from scattering. An individual impurity cannot scatter a Cooper pair without breaking the entire condensate, which costs too much energy. So now we can finally answer the question, why does resistance suddenly drop to zero at the critical temperature? Above the critical temperature, thermal energy is large enough to break Cooper pairs. You have normal electrons that scatter off impurities, phonons, and each other. Normal resistance. Right at the critical temperature, the thermal energy drops below the pairing energy. Cooper pairs start to form and condense into the coherent quantum state. Below the critical temperature, essentially all electrons are paired and locked in the coherent state. They move collectively and cannot scatter individually. Resistance is exactly zero. The superconducting transition is a second-order phase transition. The order parameter, which is related to the density of Cooper pairs, grows continuously from zero at the critical temperature. Near the transition, the superfluid density behaves as ns of t proportional to 1 minus t over tc to the power of 1/2. This explains the sharpness of the transition. Now let's see how BCS theory finally fit the experimental curve that had puzzled physicists for nearly half a century. When you plot resistance versus temperature normalized by the critical temperature, BCS theory produces a curve that matches the experimental data beautifully. Above Tc, you have normal resistance. Right at Tc, there's the sharp drop. Below Tc, exactly zero. BCS theory not only explains the zero resistance, but also correctly predicts the specific heat jump at the transition, the magnetic properties, and the isotope effect, where critical temperature depends on atomic mass. One of the most beautiful aspects is that superconductivity turned out to be a universal phenomenon. After mercury, Onnes and others found it in lead, tin, aluminum, and many other elements. Mercury has Tc equals 4.2 Kelvin. Lead has 7.2 Kelvin. Niobium has 9.2 Kelvin. Each material has its characteristic critical temperature, but the physics is the same. Today, superconductors are used in MRI machines, particle accelerators, quantum computers, and sensitive magnetic field detectors called SQEDs. There's actually another remarkable property that I haven't mentioned yet. In 1933, Meissner and Oxenfeld discovered that superconductors don't just have zero resistance, they also expel magnetic fields. When a superconductor is cooled below its critical temperature, magnetic field lines are completely expelled from the interior. The magnetic field B inside a superconductor is exactly zero. B inside equals zero. This is called perfect diamagnetism, or the Meissner effect. And here's something crucial. This is not just a consequence of zero resistance. Even a perfect conductor with zero resistance wouldn't necessarily expel fields. The Meissner effect reveals that superconductivity is a true thermodynamic phase. Magnetic field lines bend around the superconductor. They cannot penetrate. This leads to spectacular levitation effects, where magnets float above superconductors. The story doesn't end with BCS theory. In 1986, Bednorz and Mueller discovered a new class of ceramic materials that superconduct at much higher temperatures. These copper oxide ceramics, also called cuprates, can have critical temperatures above 138 Kelvin. That's still cold, but it's above the boiling point of liquid nitrogen, which makes them much more practical. Here's the fascinating thing. We still don't fully understand the mechanism of high-temperature superconductivity. BCS theory doesn't quite work. The pairing mechanism seems different, possibly involving spin fluctuations rather than phonons. This remains one of the major unsolved problems in condensed matter physics. We can measure the properties, but the complete microscopic theory is still being developed. Let's step back and appreciate what Onnes' discovery represents in the history of science. Superconductivity was not predicted by any theory. It was a purely experimental discovery that completely surprised the physics community. It dramatically revealed the limitations of classical physics. No amount of clever, classical reasoning could explain zero resistance. The explanation required fundamentally new quantum concepts: macroscopic quantum coherence, spontaneous symmetry breaking, and collective quantum states. From the experimental discovery in 1911 to the theoretical explanation in 1957 was 46 years. This shows how profoundly challenging the problem was. The lesson is profound. Nature can surprise us with phenomena that our current theories cannot anticipate. Careful experimental work can reveal entirely new physics. Let me give you a quantitative summary of the key numbers from this discovery. Critical temperature, 4.15 Kelvin for mercury. Resistance drop, more than 5 orders of magnitude. Energy gap, approximately 1.3 millielectron volts. Coherence length, approximately 50 nanometers, the size of a Cooper pear. London penetration depth, approximately 50 nanometers, the distance magnetic fields can penetrate. These characteristic length scales and energy scales completely define the superconducting state and determine its properties. Why should we care about this century-old discovery today? Let me give you several reasons. Superconducting magnets in MRI machines save lives every day by allowing non-invasive medical imaging. Modern quantum computers use superconducting circuits as qubits. Companies like IBM and Google are building quantum processors based on superconducting technology. The fundamental physics still holds mysteries. Room temperature superconductivity remains an elusive goal that would revolutionize energy transmission. The story shows how curiosity-driven basic research, like Onnes' quest to reach absolute zero, can lead to transformative applications decades later. So let's return to where we started. Onnes expected to see a smooth, gradual decrease in resistance as he cooled mercury. Classical physics gave him no reason to expect anything else. Instead, he found a cliff. A discontinuity, a phase transition that classical physics could not explain. That single anomalous measurement forced a revolution in our understanding of matter. It revealed that quantum mechanics wasn't just for atoms and molecules. It could operate on macroscopic scales. For nearly half a century, theory struggled to catch up to experiment. When it finally did, with BCS theory, it opened up entirely new areas of physics. This is science at its best. Careful measurement revealing unexpected phenomena, theoretical struggle to understand, breakthrough insight, and ultimately practical applications that benefit humanity. That resistance curve, with its sharp drop to zero, is one of the most important graphs in 20th century physics. It couldn't be fit by any classical theory. It demanded a fundamentally new quantum framework to explain. And in developing that framework, physicists created tools that extended far beyond superconductivity. The discovery of superconductivity teaches us something profound about how science progresses. Pay attention to the data that doesn't fit. The anomalies. The surprises. These are often where the deepest truths hide. Our classical expectations, however well-founded, can be wrong in spectacular ways. Nature is under no obligation to conform to our theories. Understanding comes through patience, persistence, and the willingness to completely revise our conceptual frameworks when the data demands it. That's the legacy of Heike Kamerlingh Onnes, a careful experimenter who cooled mercury to 4 Kelvin and found that resistance could vanish completely. A discovery that broke classical physics and birthed an entirely new understanding of matter.